Everyone thought the Tesla Cybertruck looked impossible to build. Not just unusual, but impractical at scale. Flat stainless steel panels, no paint, massive single-piece cast structures, and a battery that doubles as part of the frame. That combination breaks almost every standard rule in automotive manufacturing. But that is the exact point. The Cybertruck is not designed first and then figured out later. It is built around how it can be manufactured, and once you follow the process step by step, the design stops looking strange and it starts making sense. The process begins with material selection, and this is where the path splits from traditional automotive production. Most vehicles use mild steel or aluminum for outer panels because they are easy to form. They can be stamped into smooth curves quickly, and any imperfections can be hidden under paint. The Cybertruck uses ultra-hard, cold, rolled stainless steel instead. It is far stronger and more resistant to damage, but it behaves very differently under force. This steel does not want to stretch or flow into complex shapes. It resists deformation and springs back when pressure is removed. That rules out conventional stamping for most of the exterior. Instead, the process relies on controlled bending. Sheets arrive in flat form, cut to precise dimensions. From there, they move into bending systems designed to apply force along straight lines. Each panel is formed through a sequence of folds. The machine presses along a defined edge, creating a clean, sharp angle. Then the sheet is repositioned, and the next bend is made. The geometry builds step by step. The result is a surface made of flat planes meeting at distinct edges. That is not a stylistic flourish. It is a direct outcome of working with a material that cannot be shaped easily into curves without compromising its surface. Surface quality is a constant concern. There is no paint stage later to cover scratches or inconsistencies. The steel that enters the process is the same steel the customers will see. Handling systems are designed to protect it at every stage. Panels are gripped from edges or hidden areas. Robotic movement is controlled to avoid unnecessary contact. Even small marks can stand out. Once formed, these panels serve a structural role. In most vehicles, the outer body panels are attached to a separate structure. They contribute little to overall strength. The Cybertruck uses an exoskeleton design, where the outer shell carries load. That changes how the panels are integrated and how precisely they must be aligned. At the same time, a separate part of the factory is producing the lower structural components using high-pressure casting. This process starts with aluminum alloy, heated to a liquid state, typically around 650 to 700 degrees Celsius. The molten metal is injected into a mold under extremely high pressure, often thousands of tons. The molds are designed to create large, complex components in a single operation. These include the front and rear sections of the vehicle. Each casting replaces many smaller parts that would otherwise be stamped and welded together. This reduces the number of assembly steps. It eliminates numerous welds and fasteners. It also reduces variation, because fewer parts mean fewer opportunities for misalignment, but it increases the importance of each individual component. A defect in a large casting affects a significant portion of the structure. The casting process requires tight control. The temperature of the molten metal must be consistent. The injection speed and pressure must be precise. Cooling must be managed to prevent internal stress or distortion. After the metal solidifies, the casting is removed, trimmed, and inspected. Excess material is cut away, and measurements confirm that the part meets exact specifications. At this stage, the vehicle has two major structural elements, one at the front and one at the rear. The next step is to connect them, and this is where the battery becomes central to the design. The Cybertruck uses a structural battery pack built from 4,680 cylindrical cells. These cells are arranged into a rigid assembly that can handle mechanical loads. The battery is not just an energy source. It is part of the structure. The assembly of the battery pack begins with cell production. Each cell is tested to ensure it meets performance and safety requirements. Cells are then grouped and bonded together. Structural elements are integrated to provide strength. Cooling systems are added to manage temperature during operation. Once assembled, the battery pack is sealed and tested. It must meet strict standards before it is installed. During vehicle assembly, the battery is placed between the front and rear castings. It connects them, forming the central section of the structure. This creates a continuous load path from one end of the vehicle to the other. It reduces the need for additional structural components, but it also requires precise alignment. The battery must fit perfectly with the cast sections. Mounting points must match exactly. Sealing surfaces must prevent moisture from entering. Once installed, access to the battery is limited. That means quality must be ensured before installation. There is little opportunity for adjustment later. Electrical architecture is designed to support this integrated structure. The Cybertruck uses a 48-volt low-voltage system instead of the traditional 12-volt setup. Increasing voltage reduces the current needed to deliver the same power. Lower current means less heat and smaller wiring. This simplifies the wiring harness. Wires are thinner, bundles are smaller, routing becomes easier. There are fewer connectors to install, which reduces complexity and potential failure points. Communication between systems is also streamlined. Data is transmitted through faster networks, reducing the need for extensive wiring across the vehicle. This further simplifies assembly. For propulsion and charging, the truck uses a high-voltage system. Higher voltage allows for more efficient power delivery and supports faster charging. It also reduces the size of the cables needed to carry energy. With the structural core and electrical systems prepared, assembly moves into integration. The front casting, rear casting, and battery pack are joined together to form the main body of the vehicle. Joining methods are selected based on the materials involved. Structural adhesives are used to create strong bonds across large surfaces. Fasteners and welds are used where necessary. Each connection must handle mechanical stress and environmental conditions over time. Precision at this stage is critical. These components define the geometry of the entire vehicle. Any misalignment would affect the fit of panels, also the operation of systems and the overall performance. Once the core structure is complete, the stainless steel panels are installed. This is where earlier steps become visible. Panel gaps must be consistent. Edges must align cleanly. What is assembled at this point is final. That forces strict control over tolerances from the beginning of the process. Skipping the paint shop removes one of the most complex parts of traditional manufacturing. It eliminates multiple steps, reduces energy use, and simplifies the overall process. But it shifts responsibility to earlier stages. Surface quality must be maintained throughout forming and assembly. As the exterior comes together, internal systems are installed. Suspension components are mounted. The Cybertruck uses adaptive air suspension, allowing ride height to vary. This requires integration of air springs, compressors, and control systems. Steering introduces another change. The truck uses steer-by-wire, removing the mechanical connection between the steering wheel and the wheels. Sensors detect input, and actuators control movement. Rear wheel steering adds further complexity. The rear wheels can turn slightly, improving maneuverability. This requires additional hardware and precise calibration. Interior assembly follows. Seats, displays, and controls are installed. The design reduces the number of individual components by integrating functions into larger systems. This simplifies assembly, but increases reliance on software. Software integration is a key step. Systems are loaded with firmware. Calibration ensures that steering, suspension, and power delivery behave as intended. Sensors are checked. Communication networks are verified. Testing completes the process. Electrical systems are powered up. Mechanical systems are exercised. Diagnostics check for faults. Surface inspections ensure that the exterior meets visual standards. Across the entire manufacturing sequence, a consistent pattern emerges. Complexity is reduced by combining functions into fewer parts, but each part becomes more critical. There are fewer opportunities to correct mistakes. Each step must be executed with precision. The material does not hide flaws. The structure depends on accurate alignment. The systems rely on tight integration. Every decision builds on the one before it. This is what defines the Cybertruck manufacturing process. It is not about refining existing methods, it is about reorganizing them. The stainless steel shell dictates forming. The casting reduces assembly steps. The structural battery ties everything together. The electrical architecture simplifies wiring. Each choice removes a layer of convention and replaces it with a stricter requirement. The result is a process that is direct, controlled, and highly integrated. What makes it compelling is not just the technology involved, but how tightly everything connects. The shape of the truck is a reflection of the process. The process is a response to the material, and the material forces the entire system to operate differently. In the end, the Tesla Cybertruck is built through a sequence that leaves little room for improvisation. Each stage feeds directly into the next, locking in decisions early and carrying them forward without the option to adjust later. Every component carries more responsibility. Parts that would normally play a minor role now define structure, alignment, and performance all at once. That raises the stakes at every step of the process. The entire system depends on precision from the first step to the last. There are no easy corrections, only a chain of tightly controlled operations where accuracy is built in from the beginning.